not here can hear it. So so we're recording this, so just know when you guys ask a question, you can chat it or whatever, and that's fine. Okay, so and you can stop me at any point if I'm going too fast. So here's kind of a nuclear chem overview. I'm gonna close that. And make that small. Goodness. Okay, so just for what you remember, so I think like a fourth of the class has sent me their exams, and those are due tonight at midnight. And so for the nuclear chemistry unit, it's all of the chapters, so 10A, 10B, and 10C. The homework, however, is limited to problems in A and B. We didn't assign any problems for 10C. So those are the problems there, and I'll kind of link them back to what parts they are, and we can talk about ones that seem a little bit difficult. The concepts in this unit were determining isotopes, isotopic dating, nuclear decay, alpha, beta, gamma, predicting and identifying nuclear stability, being able to not predict, but understand and kind of, I guess, predict or suggest some kind of nucleosynthesis. We talked about activity, so that's nuclear decay, the units of activity, nuclear binding energy, the difference between fission and fusion, and then the mass defect. That's probably me making noise. So then skills are completing and balancing nuclear equations. So that's decay or capture, distinguishing between alpha, beta, and gamma radiation, predicting the stability of isotopes and decay mechanisms, using half-life to predict the amount of sample and the age of objects, and then using nuclear binding energy from nuclear mass and the energy released in nuclear fusion. So let's talk a little bit about why we're interested in nuclear chemistry. So basically the amount of energy possible from a nuclear reaction is much, much higher than energy used in normal fossil fuel kind of energy. All of the elements in the universe are products of nuclear reaction. Nuclear medicine, so radiation therapy, is commonly used to treat and also identify or detect diseases. And then you've got these different nuclear isotopes used in kinetic experiments. So a lot of the last unit, we were like, here's the first step, here's the second step. So the reason we can claim those things is that we've done nuclear isotope. So then the strong nuclear force, again, is why the protons and neutrons stay together in the nucleus. That's the force that we use to rationalize why you've got this highly charged proton that stays next to a highly charged proton when everything that you've learned so far about electrons is that they repel each other. And then the other thing that we've talked about is alpha particles. So these are these large helium particles, beta particles, that are, a negatively charged particle, positrons, which is the positively charged particles, and then gamma rays, which have no charge and are the smallest, and kind of thinking about how they're attracted to an electric field. So the alpha particles are slightly attracted to a negative field. The beta particles, which are smaller in mass, are highly attracted to a positive field. So then a little bit more about nuclear reactions and isotopes. So isotopes are always going to have the same number of protons with different number of neutrons. So if you have like hydrogen and deuterium, they both have one proton, but deuterium will have two neutrons, whereas hydrogen will have one. And then here's your carbon example. So then nuclear reactions is such that the isotopes of the same element undergo different nuclear reactions. So you're changing protons and neutrons in a nuclear reaction. That's different than a chemical reaction because we're not changing neutrons or protons. In a chemical reaction, we're just changing electrons. And nuclear, you're actually changing the identity of the element that you're looking at. So these are examples of alpha decay, beta decay, positron emission. These are the ones where if you're balancing or predicting these types of reaction, your particle is a product. And so when you're balancing the reactions, you need to make sure that the mass the mass number match up, and then the proton numbers add up as well. So that's kind of how to balance those reactions and think about it. And then the only other one, electron capture, is where you have an electron on the reactant side because it's reacting with that element to produce what's going on. So then there was a little bit about stability of the nucleus of different elements. And so there's kind of this band of stability where if you have an atomic number less than 20, then your protons and neutrons have to be the same. Kind of in between, you need more neutrons than protons. And then if you have a higher atomic number, basically all isotopes are unstable. And this kind of makes sense to me because, again, if you have a bunch of protons in that nucleus, it should be unstable. So the neutrons being higher than the protons kind of like dilutes that effect a little bit. That's not a real thing. So then if you're above this band of stability, these are neutron rich. Below, you've got proton rich. And so they kind of decay differently. So if you're above the band of stability, you're gonna basically decay. Your neutrons are gonna turn into protons and electrons, right? So you're gonna like basically lose a beta decay. And then here, if you have proton-rich nuclei, they're going to decay so that their atomic numbers increase. So you're going to have alpha decay. So there's a lot more ways that you can decay below the band of stability as opposed to above the band of stability. So then this next part was just kind of about ionizing radiation, and that the different electromagnetic radiation that has good penetrating power is a problem and is toxic for our bodies. And in terms of like how they go through, the body is dependent on their charge and their mass, and then of course gamma can just go through anything because it doesn't have a mass or a charge. And so then we talked a little bit about isotopes. So the isotopes are used in a number of different applications. And then we talked a little bit about activity. So this is the part that is pretty familiar because you're just all decay happens through a first order rate law. So rate of decay is just going to be your rate constant times how many atoms you have. And so this is your half-life, natural log of 2 divided by k, and then you can basically, take e to the negative kt times your initial number of atoms to get your atoms that are left, right? And then your activity is the rate of decay, which is just your rate constant times the number of atoms that you have. So then there was a couple of examples of how to use this. I went through that really fast. So this is just kind of like a decay process. How long does it take to decay? Another way to ask this problem is how much is left after a certain time. And again, you're just using the rate laws to kind of plug everything in, plug in your constants, look at ratios of what you have, plug in your time, using your half-life to get your rate constants and stuff like that. So that's one of the examples. There was another example. So we talked a little bit about nuclear energy and how you can get energy from the mass defect. So E equals mc squared is referring to the mass defect of something that has like undergone fission or undergone fusion. And so then we talked a little bit about how smaller nuclei are more likely to undergo fusion, larger nuclei are more likely to undergo fission. Fission is a breaking up of particles, fusion is a coming together of particles. And if you look at this chart, the main point of this chart is that iron has the highest binding energy or the most stable nucleus. And so everything tends to fuse and fizz down to, I don't think fizz is a word, down to iron. Because that's the most stable, right? So in terms of thinking about thermodynamics, like that's the most stable nucleon, and so things are gonna tend to move towards that way. So then this is an example of how to find that energy related from a process. Where you've got fission happening. So here's the fission of uranium into barium and krypton. And so calculate the energy when it undergoes fission. So here's all your masses of your particles. You've got to basically find your mass defect, which is a fancy way of saying your difference in mass between your products and reactants in a nuclear reaction. That's going to be an AMU, so we got to convert that to kilograms. We can then find E equals mc squared. So here's my mass defect. Here's c squared. that gives us a number that we then need to multiply by the number of nuclei that we have in 1 gram. So we're going to take, you know, our nuclei that we have in the uranium, and then convert that over to that, and then multiply that number, the number of nuclei we have, times the mass defect times c squared, and that gives us this number, 7.3 times 10 to the 10 joules. So when you think about something like methane being burned, usually the energy associated with burning fuels is like kilojoules, so 4,000 kilojoules or something. So this is still like 3 times more than fossil fuel energy generation. We talked a little bit about nuclear power generators, kind of how you've got this is your reactor core, these are your control rods. The control rods, I don't know if we talked about this, but control rods basically will absorb neutrons. So when you think about fusion reactions, which we talked about here, there was kind of chain reactions where you talk about neutrons that are coming off of these reactions, and those neutrons hit other nuclei, and then those nuclei continue to split. And so if that happens too fast, you get a runaway reaction. So these control rods actually will absorb neutrons and stop those chain reactions from happening too fast, which is really good. And so then that generates really hot material, which then you can use to create steam, which then can generate your power for a turbine. So that was really fast. I did it in 13 minutes. I said I was going to do it in 15. 13 is very fast. So questions from you guys. I'm going to pull my chat screen up and my participants screen up. So what questions do you guys have about this chapter? Or if you have other questions, you can answer those too. Anything I need to go through slower? I wasn't watching my, I wasn't watching if you guys were saying go slower, go faster. Okay, so who's got a question? Kim just emailed me, thank you. I will go look at that. So questions are, oh, let me tell you about homework actually. So, because that is what I said I would do. Let me look at this. Let me look at this thing that I was just sent though. Okay, we'll have to look at that. Okay, so so in your homework, let's talk about your homework real quick. So according to my notes with your homework, problem 2 of 10A requires you to think way back to your Chem 112 days, and remember that E equals h nu, right? So Planck's constant times the frequency, and then you can also get the frequency from the relationship of the speed of light and the wavelength, right? So that's going to be problem 2. Problem 6, 8, and 10 are all about this concept of balancing nuclear equations. So, and they're asked in a couple of different ways. So can you show what alpha decay is? Can you show what beta decay is? Can you show what gamma decay is? And do you know what side to put that on? If you have to fill in a blank of some kind of emission, do you know which decay it was or what was emitted in terms of particle sizes, particle identities? And so that's problem 6, 8, and 10. They're basically all the same concept, but just asked in a different way. Problem 16 is now, do you, I see the question. I will go through that question. So problem 16 is kind of a cascade of steps now. So if you can do it once, can you do it many, many times? So if I say, you know, element A of isotope such and such undergoes this many beta decays, a gamma decay, another alpha decay, etc. Can you like count up the decays and figure out what's going on? So it's just kind of a cascade of steps. And then 18 is another way to ask nuclear decay questions. So all of chapter A, all of section A is mostly, can you balance nuclear reaction using appropriate mass and charge. Okay, so 10B, problem 2 is evaluating half-lives given rate constants. And so that's pretty straightforward. You just have to remember that T1/2 is the natural log of 2 over K and kind of go through that. Problem 4 is this activity problem that seemed pretty difficult. And so we can go over that if we need to, but I'm sure Kimberly will go over it in the help session on Friday, on Thursday, tomorrow, right? Tomorrow, probably. And then problems 6, 10, and 12 are all, can you use the first order decay rate law to figure out what's going on. So that's what all of those problems are. Okay, so while you guys are thinking of your questions, we have a question about, can you go through a binding energy calculation? So the one that was in the lecture was example 10C2. So let's find a different one. Calculate the energy, calculate the binding energy per nucleon. Can you go through a binding energy calculation? So we'll calculate the binding energy per nucleon. And then we'll do a calculate energy release per gram problem. So let's do this problem. Let me share a screen. Put in a new slide. Oops. And then while I'm doing this, if you guys want to text me or text Esteban, then we'll be able to see the chat. Let me quickly make Esteban a co-host since he's not yet. Okay, so I'm going to work through this problem, and then if you guys have other problems that you're thinking about, then then just interrupt. What is happening? Let's go here. Okay, can you guys see that? I think you can see this slide here. Okay. So, text box. So the question is, calculate the binding energy per nucleon for 62 nickel, which has 61.928. 346 mu. Okay, so we need a few things to be able to do this. We need this value. This is the thing we need because we need to be able to convert our energy over. And then make sure I do this right so we don't confuse anybody. So you're going to calculate the difference in mass between the nucleus and the free particles from which they form. So for all these problems, you need a periodic table. So let's look at nickel. Oh, terrible. Nickel has 28 protons. So nickel is protons equals 28. And so 62 minus 28 is 34 neutrons. So that is what I have going on. So the difference in binding energy is going to be, this is the actual mass of this nickel nucleon, but there's going to be a difference between this nucleon versus the masses of how many protons I have and how many neutrons I have, right? So to do this problem, I also need the mass of a proton and mass of a neutron. So let me find those values. Proton, neutron. So the mass of a proton is 1.0078 mu, which is this unit we're using. And the mass of a neutron, whoa, I always spell received wrong, so neutron seems to also be an issue for me, 1.0087 mu. So, so then what we're going to do is we're going to take 28 times 1.0078 plus 34 times 1.0087. And that is going to be equal to 1.0078 plus 34 times 1.0087. Why those are like just exactly different is pretty bad. So 62.5142. Which better not be the same number. Good. Okay, so this number is what my mass of my nucleon should be if it was just a combination of protons and neutrons. But my binding energy is what kind of that mass defect is, which is the difference in the energy of them. And so this gives me, so here's my 62 nickel, which is 61.92834 minus this calculated number 62.5142, and that number is my mass defect 834. And I think that we're gonna use the absolute value of it at some point, but for now it's equal to negative 0.58586. I don't think I get to use that many units. I think I only get to use this many units because I kept that many there, so that's a subtraction. So now I've got my E equals mc squared, but I can't use mu because that's not the right units for energy. So, so that's going to be this, and then I think it's times, yep, times 1.6605 times 10 to the negative 27 divided by mu. So that gets rid, sorry, of my mu, and then times 3.0 e to the 8 squared. So this should give me my energy number. So negative 0.5859 times 1.6605 times 10 to the negative 27. I feel like my units are going to be bothered. 8 squared. So this is negative, but we're going to take the absolute value. So this is equal to 8.76 times 10 to the negative 11. Okay, so that gives me that number, but then if you want to know like how much in a gram of it or something, then you have to convert it. You have to do a little bit more. You have to do it per nucleon, right? Okay, so this is the part that's sometimes unclear to me. You get this number, and this is the number that students want to answer. But this is the number binding energy for a nucleon, which no, this is the total number. This is the joules, not per nucleon, sorry. And so you have to divide this by how many nucleons you have, and you have 62 nucleons in this case because it's 62. So we're going to divide it by 62 nucleons, and then that gives us our answer in joules per nucleon. So that gives us our binding energy for this. So then let's say in a different problem it wanted to know how much energy question mark in 1.0 gram of material. And so in that case, you would find out how many nucleons per gram, and then multiply it by that many nucleons, and then that would give you your energy. So that is how you go about answering that question in terms of what's going on. Okay, other questions? Yeah, you're welcome. That was a rough one for me because I'm not as familiar with binding energy in nucleons. So sorry about the slowness. Okay, other questions you guys have? I think I found. No. Oh, I've only got 4 of you left. 3, 4. 1, 2, 3, 4. 4 of you are here. Do you guys have questions? Okay, I'm going to stop recording then because this is a long